AI applications are scaling outward at a blistering pace, demanding massive physical infrastructure to support them. We're past testing isolated tools. Between 2024 and today, the debate over whether AI delivers real business value ended. The market has proven the necessity. Demand risk is entirely dead. The core threat facing enterprise leaders today is execution risk. Deploying AI at scale means navigating uncertain supply chains, timelines that stretch further every quarter, and the hard physical limitations of building out power and cooling capacity. This execution risk is compounding across the industry. Major players are dealing with high pipeline exposure, where massive amounts of promised compute are delayed by geopolitical tensions disrupting hardware availability. Winning the AI race has shifted away from who can generate the most compute demand. Success is now strictly defined by who can physically execute their architecture the fastest. This brings us to a pervasive misconception in enterprise IT, the belief that simply acquiring massive clusters of GPUs guarantees a successful AI deployment. Heavily funded AI initiatives stall, not in software, but at the infrastructure layer, where disparate components create severe bottlenecks. Fragmented infrastructure causes unpredictable performance, vendor lock-in, and data gravity walls. Proper execution requires a seamless, continuous ecosystem of development, training, and orchestration. Without a vendor-neutral infrastructure foundation acting as the base layer to support that flow, enterprises remain trapped in closed systems. The ecosystem breaks down, and the AI investment stalls entirely. We have to look at the physical engineering bedrock required to support this ecosystem. Standard retail colocation cannot deliver the flexibility or the power required to host modern AI workloads. This diagram shows a high-density server rack. Infrastructure planners are aiming at a moving target to maintain pace with the Silicon roadmap, meaning facilities must prepare to support 600 kilowatt rack densities by 2027. This generates extreme heat that traditional air cooling cannot mitigate. To extract that heat, we introduce highly specific cooling architecture. This involves routing chilled water loops directly into the data hall and interfacing them with a cooling distribution unit, or CDU, placed next to the IT equipment. The CDU then distributes that liquid down to the microscopic level, powering rear door heat exchangers and direct liquid cooling plates attached directly to the individual servers. Implementing liquid cooling is no longer a future state luxury or a niche architectural choice. It is the baseline prerequisite for operational survival. Once the physical bedrock is secure, the economics of deployment take over. The standard metric for evaluating total cost of ownership in this space is optimizing cost per token. Achieving positive cost per token economics means avoiding overprovisioning and hitting rapid deployment cycles of 4 to 12 weeks. Speed to market keeps the economics viable. There is a common assumption that as AI matures, inference will replace training. They are not in a zero-sum game. Demand for massive training runs and highly active inference workloads are scaling simultaneously. However, their physical architectures look very different. While model training relies on massive, centralized megaclusters of compute, inference workloads demand a distributed, proximity-driven approach. To monetize AI capabilities, your inference architecture must physically sit right next to the end user. It requires deploying nodes across distributed metros to minimize the physical distance the data travels. That distance introduces the network layer constraint. The most advanced GPUs on the market yield nothing if high-latency connections starve them of data. This captures deterministic latency. Instead of the unpredictable public internet, data routes securely between proprietary models and physical infrastructure. We can think of this as a private AI exchange. Consider the radio in your car. Standard FM or cellular signals drop out in dark zones, but satellite radio provides a premium, built-in capability that delivers continuous high-definition audio everywhere, bypassing spotty public networks entirely. A private AI exchange operates the exact same way for enterprise data. It orchestrates high-speed connections across multiple public clouds and proprietary data centers without ever exposing that workload to public internet traffic. Because of data gravity, an enterprise with petabytes of information cannot afford to continuously migrate that data into the public cloud. They must architect a network that brings the cloud and AI compute directly to the data. This matrix outlines a practical blueprint. IT leaders must evaluate their infrastructure partners against these 4 specific criteria to ensure they are building production-ready AI factories rather than just isolated pilot clusters. First, scalability and sustainability. The facility must be capable of handling 10-plus megawatt modular scaling as workloads grow, while explicitly utilizing energy-optimized hardware and cooling to minimize the carbon footprint. Next, interconnectivity and neutrality. The partner must guarantee deterministic latency to solve for data gravity, and they must provide an open, neutral meeting ground to prevent lock-in to any single hardware or cloud vendor. If an infrastructure provider fails to deliver on any one of these 4 quadrants, they inject unacceptable systemic execution risk into the enterprise's entire AI deployment. Innovation in software, models, and algorithms will hit a hard ceiling without the physical capacity to orchestrate it at scale. Future-proofing your enterprise relies on securing the right physical space. Success depends entirely on ecosystem-proofing the neutral physical infrastructure your AI runs on today.